This is lesson 23. We're going to discuss square root and cube root functions. I've divided this lesson into 4 parts. First, we're going to see how to solve square root equations, then how to graph square root equations, then we'll look at cube root equations being solved, and finally we'll look at the sketching of cube root equations. Let's start out with a very simple square root equation. Let's go to the board and take a look at a very easy equation to solve. The square root of x plus 3 equals 4. And again, a square root equation obviously is an equation in which the variable, in this case x, appears inside a square root. Well, the first thing we want to do is isolate the square root. Just as many lessons ago we isolated the absolute value, we isolate the square root, and when we've done that, we square both sides. Squaring a square root gives you what's inside. Squaring 4 gives you 16. And of course, you now have a simple equation, one letter, linear equation like we did way back at the beginning of this series. We subtract 3 from both sides, and we get x equals 13. And if we check, plug the 13 back in, 13 plus 3 is 16. The square root of 16 is 4, so it checks. An important thing to remember is when we have a square root in an equation, we're always talking about the positive square root, or if it's the square root of 0, obviously 0. If when we're solving an equation, as we did with quadratics, we take the square roots of both sides, so we have like x squared equals 16, we take the square root of both sides, we get x equals plus or minus 4. But for example, in the problem we just did here, when we took the, when we squared, we simply said that's 16. We went back over here to check. When we said the square root of 16 was not plus or minus 4 because that's part of the equation. Only when we're actually taking the square root of both sides of an equation do we worry about the plus or minus. Hopefully you understand that difference. Let's look at a little bit more complicated equation in our first visual. The square root of x plus 3 equals x plus 3. Now think about what that means. What that means is the square root of some number is equal to the number itself. You may say, I don't think that can occur. Well, let's find out, because remember, there are equations where the answer is there is no answer. In fact, I think we'll run into one fairly soon. What did I do here? Well, in the second line, which is highlighted, we squared both sides. And again, x plus 3 squared does not mean x squared plus 9. It means x plus 3 times x plus 3, which is x squared plus 6x plus 9. We are now solving a quadratic equation. It keeps coming back to us. What do? We get everything on one side equal to 0. That's highlighted on line 3. We factor the quadratic and set each factor equal to 0. And thus we get our solution as shown in the last line, x equals negative 3 or x equals negative 2. Of course, we need to check. So let's go to the next visual where we check. First, we'll check x equals negative 3. We replace the x with negative 3, solve the equation. Of course, we get the square root of 0 equals 0, and that checks. We then replace x with negative 2, and we wind up with the square root of 1 equals 1, and that checks. So therefore, both answers, negative 3 and negative 2, are answers to this square root equation. Let's take a look at the next visual and another square root equation. This equation looks very similar. That is, you have a square root equal to a linear term. The square root of x minus 3 equals x minus 5. We square both sides. We have a quadratic. We move everything to the left side. And we get quadratic equal to 0. We factor, set each factor equal to 0, and as seen in the last line, we get the solution x equals 4 or x equals 7. In the next visual, we show the check of these two solutions. The square root of 4 minus 3, again, we replaced x with 4, which is 1, equals 4 minus 5. But wait a second. 4 minus 5 is negative 1. Does 1 equal negative 1? No, it does not. X equals 4 is not a solution to the original equation. And ever since we began solving equations in this series, I've always said check in the original equation. x equals 4 was a solution to the quadratic, but not to the original equation. And that happens quite often in square root equations. We then check x equals 7. The square root of 4 equals 2, as seen in the second line on the visual, and x equals 7 is the only solution to our square root equation. Let's take a look at another one, again with a little different wrinkle in it. The next visual shows us a square root equation where we now have something added outside the square root, and we've even multiplied the square root by, in this case, 2. Well, what do? Again, we isolate the square root first, which is what we've done. On the second line, we have subtracted 19 from both sides. On the third line, which is highlighted, we have divided by 2 to get to a square root equation that says the square root of x minus 5 equals negative 7. What do we then do? Well, the next visual shows us what to do. We continue on. We square both sides. Notice negative 7 squared is positive 49. We then solve for x. We get x equals 54. We then check our only solution, which is x equals 54. We replace the x with 54, and we get 2 times 7, which is 14, plus 19 equals 5. Now, I don't know how bad your arithmetic is, but I don't think that 14 plus 19 equals 5 in anybody's world, and therefore that x equals 54 does not check. In fact, the answer to our original equation is that there is no answer, or no solution. All right, we've looked at various types of square root equations, and as before, we generally use our knowledge of solving equations to help us sketch graphs. Because remember, the word graph means picture, and in my mind, when we start building models using functions to explain real-world phenomena, to predict what's going to happen in real-world situations, we need to be able to picture that, and therefore a graph is worth the old 1,000 words. And to sketch or draw that graph, we need to know something about solving equations. So what we're going to look at now is sketching square root equations, or if you will, square root functions. Let's go to the easel and take a look at the very basic square root equation. Okay. Let's have y equals the square root of x. And since we, at this point in time, may not know a whole lot about this equation, let's just plot some points. One thing it's important to understand is that x cannot be negative, because we have no imaginary locations here for our y-axis. We can't plot the point x equals negative 4, y equals 2i. So therefore, x can be 0 or positive. When x is 0, y is the square root of 0, and that is 0, 0, which is a point right there. When x is 1, y is the square root of 1, and that is 1, right? So we'll plug 1, 1. I'm going to use 2 boxes here. I don't know if you can see these blue boxes. I'm going to use those boxes. 2 boxes equals 1, just to expand our picture. All right, then let's see. We could put in 2, but many people don't walk around with the knowledge of the square root of 2 in their heads. So let's pick another square number that we can take the square root of. How about 4? Let's see, 1, 2, 3, 4. There's x equals 4. And the square root of 4 is 2, so that goes up here. And you can kind of see what's happening. To get to a y of 3, we're going to have to go out to an x of 9. And therefore, we get a graph that looks like this. It's curved, but it really is, as we go here, it starts to settle down, and it rises, but slower and slower and slower. And there are many things in the real world that do that. Increase very rapidly at first, sort of level off, and keep increasing, but increase at a slower and slower rate. By the way, if you turn your head sideways, you might notice that this looks kind of like 1/2 of a parabola. And it should, because y equals the square root of x is the inverse function of y equals x squared. So that the fact that it looks like a parabola makes a whole lot of sense. The key thing we want to take away from this sketch is this endpoint. In square root equations, in graphing square root equations, there appears to be an endpoint. And the reason is whatever is inside that square root cannot be less than 0. So what we're going to do is to find an endpoint is solve what's inside the square root for 0. Here it was easy. X equals 0, so x equals 0, and plot the point, knowing that should be the endpoint of our sketch. Okay, it says here the next thing we need to do is to take a look at a square root function a little more complicated than the square root of x. So our next visual shows us that we have y equals the square root of x plus 4 minus 3. Again, and I hope you're used to this by now, we're going to go through a step-by-step process to graph these functions. And the first thing we've always done is look for the y-intercept. The y-intercept for square root functions is no different than the y-intercept for any other kind of function. It's simply where x is 0. When x is 0, y is negative 1. That is the square root of 4, which is 2, minus 3 is negative 1. Then we look for the x-intercept or x-intercepts. In this case, as in all cases, the x-intercepts occur when we set the function equal to 0. It's the values of x that make the function 0. So this is why we had to be able to solve square root equations. So back to the visual on the line there at the x-intercept, we take the equation, the square root of x plus 4 minus 3, set it equal to 0. Now we need to solve that. The next visual we do that. In the next visual we've solved the square root of x plus 4 equals 3. We square both sides and we get eventually x equals 5. And at the bottom of that visual we can see we've plotted 2 points. We've plotted the y-intercept 0, negative 1. We've plotted the x-intercept 5, 0. That's just 2 points. We need a third point, and that third point is going to be our endpoint. Remember from the easel, we saw that what's inside the square root can be no less than 0. So in the next visual, we seek out the endpoint. We take the square root and we set it equal to 0. And we solve for x and we get negative 4. We replace x in the original equation with negative 4. And we get y equals the square root of 0 minus 3. So when x is negative 4, y is negative 3. That is our endpoint, or you might say the beginning point. And we know what this square root should look like. It should look like half a parabola laying on its side. So the next visual shows us the third point, the endpoint sketched or plotted, and then the sketch of the curve that begins at the endpoint and goes through the y-intercept and then the x-intercept and continues out. Notice the curvature. Notice again, if you turn your head sideways, you can see it looks like one side of a parabola. Okay, let's take a look at another equation to be graphed, and that is on the next visual, y equals 4 minus the square root of x plus 9. What is different about this equation? How often have I asked that particular question? It's a very important question to ask, because by asking that question, it helps us analyze. When we see something for the first time, when we learn something, we can put that as a pattern. So when we see that type of pattern again, we'll know what to expect. In general, in doing things, if we say, what's different about this, or what do we recognize about this particular problem, in this case, this particular function, it really helps us use everything we've learned that's relevant in the past to solve this particular problem. So it's not only good in algebra class, it's really good in real-world problem solving. All right, we have this equation. What's different is there's a negative in front of the square root. We have 4 minus the square root of x plus 9. Again, as indicated on the second line, which is highlighted for you, we seek out the y-intercept. When x is 0, y is 1. On the next line, we seek the x-intercept. We replace the y with 0, and we solve, again, calling upon our ability to solve square root equations, and we wind up with x equals 7. And, of course, if you check, by the way, in that equation, you get 4 minus 4 equals 0. So, again, we should always be checking our equations when we have square roots in them, and therefore the x-intercept is 7, 0. The next visual shows us those 2 points. 0, 1, and 7, 0. Notice that something is different. In the past, these square root equations we've sketched, as we went from left to right, the graph rose. That is, it was getting higher, it was going up. Here it appears, if we connected the 2 points, even with a line, that line will be sloped down. We know it's going to be connected with a curve, and perhaps that's the effect of that negative in front of the square root. In fact, there's no perhaps about it. That's exactly right, and it's something we'll see when we get one more point. And what's that one additional point we need? We need the end point. The next visual shows us getting the end point. Once again, at the top of the visual, we see the original function, y equals 4 minus the square root of x plus 9, and we look at the end point. The end point occurs when what's inside the square root is 0. So we said x plus 9 equal to 0, and we solve for x. Again, we're back to a very simple linear equation, something we did way back at the beginning. And we get x equals negative 9. Once we get x, we want to get y. We plug the negative 9 into our original equation, and y equals 4. So our end point is negative 9, 4. Now, there is one other thing we can do. Let's just say, after you've plotted this point, you don't feel comfortable drawing the curve, for whatever reason. As in past situations, you can always plot points. We saw that, for example, in those not-so-easy rational function sketches. Plotting points can be very helpful. And if you feel a little insecure, don't be afraid to plot points. Plotting points will always tell you you're right, or if there is an error, will indicate you need to go back and check your work. So let's go ahead and plot the end point, and in the next visual we do that, and we see the 3 points plotted, the negative 9, 4, the 0, 1, and the 7, 0, and we draw in our curve. Our curve begins at that end point and goes through the y-intercept, through the x-intercept, decreasing and as a curve. And again, if you turn your head sideways, you can see that this represents 1/2 of a parabola. And typically, that's the kinds of graphs we generally get with square root functions. Although the next one we're going to do is going to be a little bit different. And isn't that just like me to put something in a little different? But again, that's the key thing that mathematics teaches us. Just when you think you know something, someone comes up with a little wrinkle that changes it. That doesn't mean you forget everything you know. That simply means you don't jump in with both feet without doing a little analysis. And if you use the proper methods, which of course is based on analysis, you will generally get the right answer. You will not be fooled by past experience alone. So let's look at the next visual and see what is different about this function. We have y equals the square root of x squared minus 16. What do you see that's different? I hope you said that what's different is that there's an x squared term. In the past, all our x terms were simply linear, just x. Here we have x squared. What are we going to do? Well, we could cry. That would be kind of silly. Or we could go to the visual and see exactly what we're doing, which is the same thing. Find the y-intercept. Wait a second. When we replace x with 0, we get the square root of negative 16. That's imaginary. It's 4i. But the fact is, being imaginary, it doesn't appear on this graph paper, which means there is no y-intercept. Is that terrible? No. It's just what happens in this particular function. Then what do we do? We seek out the x-intercept. Well, the x-intercept is obtained by setting the function equal to 0, and we have the square root of x squared minus 16 equals 0, and that's highlighted. And then we solve that, we get plus or minus 4. Remember, because we're solving x squared equals 16, and we're taking the square root of both sides of the equation, both sides, we get the plus or minus answer. Plus or minus 4, so we have two x-intercepts, 4, 0 and negative 4, 0. Well, the next thing to do is to look at the endpoints. And the next visual will show us how to do that. And simply we take what's inside the square root, set it equal to 0, and you'll notice we get the same points as we had for x-intercepts. Those points are sketched on the graph at the bottom of the visual. But the problem is, are you prepared to draw a curve right now with 2 points? I don't think so, and in fact, we have no idea what happens. We know that this curve does not cross the y-axis. How do we know that? We know that because there's no y-intercept. So what we need to do is plot some points. So in case of in the past we said we could plot points to help us feel secure. Now we need to plot points to figure out what is going on. The next visual shows us how we plot some points. We just picked an x. The x should be selected so that when you square it and subtract 16, we get a number that we can take the square root of. For example, if we put in x equals 6, we would have gotten 36 minus 16, which is 20. The square root of 20 certainly is on your calculator, but it's an approximation. It's certainly not a whole number. I chose 5 because 5 squared minus 16 is 9, and the square root of 9 is 3. We also put in negative 5. Negative 5 squared is 25, minus 16 is 9. So when x is negative 5, y is also 3, the square root of 9. And we've plotted those 2 points. And notice what we have. We have 2 curves, if you will. And in fact, if you turn your head sideways, these 2 curves sort of look like one side of an up parabola and one side of a down parabola. And perhaps in your Algebra 2 course, although I won't be covering in these tapes, you might lightly cover something called conic sections. You will certainly do this later on in senior mathematics or college algebra or pre-calculus, and you'll talk about something called an hyperbola. And this is sort of half of hyperbola. Okay, so that was a little different, but again, by plotting points, we were able to figure out exactly what our curve looked like. All right, I think it's time to start looking at something just a little bit different. How can we, is there anything left? Yes, I think so. Let's go to the board and look at a very special circumstance. And that is y equals the square root of 9 minus x squared. Now, what's different about that? Well, it has an x squared, but that's not, we just had one with an x squared in it. It's that it's minus x squared. Now, that's going to change what the graph looks like, believe me. What are we going to do? The same thing. The x-intercept, when x is, let's start with the y-intercept first. The y-intercept is when x is 0, and when x is 0, y is 3, since the square root of 9 is 3. And then we're going to take a look at the x-intercept. Will set this equal to 0. And we solve, we square both sides. And of course, 0 squared is still 0. We wind up with 9 equals x squared, or x equals plus or minus 3. Once again, we are taking the square root of both sides of the equation, so we get plus or minus. So therefore, we have x equals 3, y equals 0, x equals negative 3, y equals 0. These points look a lot like this, but they're 3 separate points because, of course, this is 0, 3, this is 3, 0. Our next visual will show us the plot of those 3 points and the sketch of the curve. Notice it looks interesting. Why does it look interesting? What shape is that curve? Well, it's drawn, you'll notice, so it looks like half a circle. And it should look like half a circle because that's what it is, a semicircle. That is a semicircle whose center is at the origin at 0, 0. Notice the radius is 3 because 3, 0 is 3 units away from the origin. 0, 3 is 3 units away from the origin, and so is negative 3, 0. Again, if you feel uncomfortable with this, we could plot some points, but I'll be quite frank, the rest of the points you could plot would probably involve the square roots of non-square numbers. When you have 3 points and you see they're all the same distance from point, you probably have a semicircle, or in some cases, a circle. All right. Now, in the time remaining, we want to talk about cube root functions. Cube root functions are not quite as important, but let's take a look at how we solve them. How about the cube root of x plus 2 equals 3? We solve this the same way as we did the square root functions, we isolate the cube root, which in this case is already isolated, and instead of squaring both sides, we cube both sides. Because the cube of a cube root is what's inside. The cube of 3 is 27, and we get x equals, not negative, no. We're going to subtract 2, and we're going to get 25. And 25 plus 2 is 27. The cube root of 27 is 3. And that's a simple example of a cube root function. Let's take a look at the next visual, which gives us a cube root function. We've got to do a little bit of manipulation of numbers, because we have the cube root plus 3 equals 0. We subtract 3 from both sides, and we cube both sides, as is highlighted on the third line, and we solve. We get x equals negative 20. If you replace the x in the original equation with negative 20, we get the cube root of negative 27, which of course is negative 3. Cube roots, odd roots, can be taken for negative numbers and you get a negative answer. And of course negative 3 plus 3 equals 0, so that checks. Now let's take a look at the graph of the basic cube root function y equals the cube root of x. So let's go here to the easel. And just as before we looked at the square root of x, let's take a look at the cube root of x. Y equals the cube root of x. Obviously, we place 0 in there first. And when x is 0, the cube root of 0 is 0. When x is 1, y is 1. When x, let's see, we got to come up with another cubic number. X is 8. 1, 2, 3, 4, 5, 6, 7, 8. When x is 8, the cube root of 8 is 2. The next point will be 27, 3. That's off the easel. But remember, we can put negative numbers. Let's put a negative 1 in. The cube root of negative 1 is negative 1. And of course, the cube root of negative 8 is negative 2. 1, 2, 3, 4, 5, 6, 7, 8, negative 2. And what we have is something very interesting. We have a graph that looks like this, that is rising up, hits this 0, 0 in this case, and sort of turns over, and now almost looks like a square root situation. And I put little arrowheads on the end to indicate we're going to go on forever and ever. This I call the 0 point. It isn't always at x equals 0, but it is where the curve changes. In calculus, we call this an inflection point. Very interesting. And you'll notice if you turn this on its side, you'll get something that looks like the functions we investigated when we looked at polynomial functions, like the cube xy equals x cubed. All right, let's take a look at a sketch of a cube root function. The next visual shows us y equals the cube root of x minus 8 minus 1. And on the screen you can see the y-intercept is obtained, the x-intercept is obtained, the y-intercept is 0, negative 3, the x-intercept is 9, 0. We've plotted the points on the next visual, 9, 0 and 0, negative 3. Is that enough to graph a cube root function? The answer is no. We need what I call the 0 point, the point where the curvature changes. Well, how do we do that? Well, that occurred in our original graph at x equals 0. Let's see what makes what's inside the cube root 0. Let's go to the next visual. And the next visual shows us the original equation, y equals the cube root of x minus 8 minus 1. And we set what's inside the cube root, x minus 8, equal to 0. That's why I call it the 0 point. It's a lot like the end point in those square root graphs. We solve for x, we get x equals 8. But remember, this is a point, so we replace x in the original equation with 8, and we get y equals negative 1. Let's look at the next and last visual, which shows us an actual graph, or a sketch of the graph, using the 3 points. The x-intercept at 9, 0, the y-intercept at 0, negative 3, and this 0 point at 8, negative 1, where the curvature changes. You'll notice the sketch looks a lot like the one we did at the easel, the one that was y equals the cube root of x. It's just moved over and down. In perhaps some later course, you can look at what changes, what causes things to move to the right and left and up and down. So what we've seen in this lesson is that we can solve square root equations, but it's very important to check. We can solve cube root equations similarly, and obviously it's a good idea to check, but not as vital as with square root equations, because with square root equations, we sometimes get answers that do not check in the original equation. And graphing square root equations, we look for the y-intercept, the x-intercept, and the endpoint. Cube root equations, we look for the y-intercept, the x-intercept, and the 0 point, the point where the curvature changes. Hopefully, if you have this, if you don't, go back, replay the tape, and you'll be an expert at graphing and solving square root and cube root equations. Our next lesson, lesson 24, will cover exponential functions, something to look forward to.